Hello and welcome back. It's Kim here again, this time to discuss model development. The learning objectives for this session are for you to be able to understand how we can model different types of predictors, including binary, categorical and continuous variables. We will look at how you can model continuous predictors non-linearly, particularly in a multivariable model accounting for other predictors. And we will look at ways to perform variable selection using statistical methods. So let us think about what we're aiming to do with model development. We want to come up with a model that works well in terms of predicting well for new individuals. So by that, I mean we want a model that both calibrates well, so is accurate, and also discriminates well, so it can separate high-risk individuals out from low-risk individuals. And we'll talk more about predictive performance and the measures we use to quantify performance tomorrow and the following day. We also want a parsimonious model. So we want to keep it as simple as possible so that it's interpretable and we can understand what's in the model and how the model works. And on the other hand, we may also need to include necessary complexity to ensure that the model predicts well. So this is a bit of a balance between these two things, but we may only want to include variables that significantly contribute to improving the fit of the model in an attempt to improve the performance of the model. Now, aspects of model development are not necessarily unique to prediction modelling, but apply to any sort of modelling. So many of the elements that I'm going to discuss here may already be familiar to you. So let's first look at how we would model different types of predictors. So let's now look at how we can model different types of predictors. So if you do have a statistical background, this might be very familiar to you. The first type of variable we can consider is a binary variable. So this is one that takes one of two possible values. So for example, sex, someone would be either male or female. And when we code this, we select one of the categories to be our reference category, and that receives a coding of 0. And the other category takes the value 1. Another example of this is whether someone is a current smoker. So again, we have a binary variable because it's either a yes or a no. We select one category to be the reference, which takes the value 0, and the other category here, yes, takes the value 1. And we can also extend this coding to categorical variables with more than two categories. So if we consider ethnicity, which might have 4 different categories, white, black, Asian and other, we need to be able to code each of these categories uniquely. So we do this using a series of indicator variables now, which will be one less than the number of categories. So for our reference category here, white, all of the indicator variables will take the value 0, and for each of the other categories, one of the indicator variables will take the value 1. We also have continuous predictors that we need to model. So these examples of these are things like age, BMI, systolic blood pressure, or biomarkers. So these are variables that are measured on a continuous scale. And what you might have seen in some studies is that some researchers decide to dichotomize their continuous variables. So for example, they might classify age as less than 65 or greater than or equal to 65 rather than modeling it continuously. Other examples include biomarkers, where they might be classified as normal or abnormal, an example of which is PSA, so prostate-specific antigen levels in men, where values less than 4 indicate normal values, or values greater than or equal to 4 indicate an elevated value. And people sometimes do this because it's easier for presentation. So for example, in tables, things can be summarized by the different groups. And it also has a need when comparing survival curves. So for example, in Kaplan-Meier plots, where there is a need to categorize data in order to plot it. And it can also be easy to interpret because there's a comparison between one group and another. However, there are problems with dichotomizing continuous variables. The main one being that we immediately reduce our power to detect a relationship between that variable and our outcome of interest. because we're losing a lot of information that is useful for prediction. So by categorizing people, we're saying that everyone within that category is the same or has the same risk, for example. And it assumes that someone right at the bottom value, so for example, someone aged 30 versus someone aged 64 would be the same. On the other hand, someone who's aged 64 versus 65 is put into different categories, which doesn't necessarily make sense. So we lose a lot of power, and we might not be able to separate out between individuals at high and low risk if we do lose this information at this stage. So the key point here is that it's not necessary to dichotomize continuous predictors for the purpose of prediction modeling. Gary Collins and others also published a paper on the effect of categorizing on model performance. And here they say that they show that categorizing continuous predictors produces models with poor predictive performance and poor clinical usefulness. Categorizing continuous predictors is unnecessary, biologically implausible, inefficient, and should not be used in prognostic model development. So a very strong key message from these authors. And just one final note then on categorizing, and this is to acknowledge that clinicians may want to group individuals for the purpose of treating them differently, so for decision making. And they might want to give one treatment to individuals at low risk and another treatment to individuals at high risk. But what we would say on this is that rather than categorizing the individual predictors, so for example age or BMI, it's better to categorize the risk probabilities that we get out from the model, so to do this after the analysis rather than before. And also just to say that where treatments are linked to different risks and individuals are treated in this grouped way, these are often referred to as clinical prediction rules or decision support tools, or otherwise stratified care. And this isn't the focus of this course, so the models could be developed in the same way, but these are where the treatment decision is attached to the model. But this requires a multidisciplinary team with expert knowledge on the topic to know how to treat the different risk groups, and therefore that's beyond the scope of this course. And also with the use of clinical prediction rules and decision support tools, we would also want to evaluate the performance of this to know that it actually improves patient outcomes. So ideally these should be assessed with impact studies. So let's now look at how we can model continuous variables. I've already said that we shouldn't categorize them, so what other options do we have? Well, the first is to assume a linear relationship between the predictor and the outcome, and that's not always realistic, so we can look at modeling the variables non-linearly, and some options include simple transformations using restricted cubic splines and also fractional polynomials, which I'll discuss now. So first, if we were to assume a linear relationship, let's consider the example of age again in our AMI data. If we assume that age is linear, we just include it in the model on its original scale. So here, this now means that we are assuming that for every year increase in age, we have the same increment in the log odds of 30-day mortality. However, often in reality, these relationships may not be linear. So therefore, we consider nonlinear relationships, the simplest of which is simply to transform our variable. So some examples that are commonly used include using the natural logarithm. So here we fit log age instead of age, and we therefore assume that the relationship is linear between log age and log odds. And we can also include polynomial terms. So here we have age, and we can include a squared term, for example. And what this means is now that relationship between age and the log odds of 30-day mortality is no longer linear. However, this again might not be flexible enough for real data, and therefore may still not be flexible enough to fit the data well. Also, for binary and time to event outcomes, we can't simply plot our data like we can for a continuous outcome and see what shape the relationship takes. So we have to rely on other methods for selecting an appropriate function. So what I want to discuss now are some other methods we can use for increased flexibility of modelling nonlinear functions, and these are restricted cubic splines and fractional polynomials. So first let's look at restricted cubic splines. These were mentioned earlier by Richard for modelling the baseline hazard in flexible parametric survival models. And the first thing we need to do is decide how many knots we're going to use and the locations. So you can specify your own, but I'd recommend using the default, which is to base this on percentiles of the marginal distribution of the predictor. And this is the recommendation by Harrell. And what this does is ensure that because it's based on the percentiles, we have enough data within our different knots, so for each of those groups, and it also guards against outliers being overly influential, because we don't want these outliers to greatly affect the shape of the function. So we can increase complexity and curvature of the function by increasing the number of knots, and here are the percentile positions that are recommended by Harrell for the different numbers of internal knots. So if there were 3 knots, we would Harrell would suggest using the 10th, 50th and 90th percentile. And this is just to show you how increasing the knots affects the shape of the function. So again, just looking at age, we can see here, so 3 internal knots. We also have 2 boundary knots that occur at the minimum and maximum values. And we can see that with 3 knots now, we have slight curvature. There's not much change for 4 knots, but as soon as we increase to 5 or 6, we see that we get something that's very flexible in shape. Another option for modelling predictors non-linearly is the use of fractional polynomials. So this is much more flexible than the other polynomials I showed you previously. So for example, just simply using a squared term. And this is because it consists of a set of 8 possible powers that could be selected ranging from -2 through to 3, so a cubic function, and also includes the natural log function. And this flexibility arises by selecting 1 or more powers from this set. So if we were just to select 1 power, P1, this would be referred to as fractional polynomial of degree m. If we were to select 2 powers from this set, then we would have fractional polynomials of degree 2. And commonly we would just see degree 1 or 2. We don't tend to see higher than this, as already that offers quite a wide array of shapes. So if we were to use degree 1, so remember this is just selecting a single power from that set, we would just fit the model, so now using age to that power. And because there are 8 possible functions that could be selected, there are 8 possible FP1 functions for this. On the other hand, if we were to increase flexibility to degree 2, so this is referred to as FP2 functions, then we would select a combination of 2 possible powers from that set of 8. So here we would use the first term using the first power and the second age term using the second power. And because there are 8 functions, there's a possible 36 combinations of these 2. Now it's fairly easy to do using statistical software, so Stata or R would fit all possible powers and then select the function that fits the data best. And it's also possible to perform tests comparing the different complexities, so it will compare FP1 models to FP2 to see if you really need that additional complexity from the second term. But you might have considered that with FP2 or higher, it's possible to select the same power twice. So for example, if with the example of age, both the first power and the second power were selected to be cubic, well, it wouldn't make sense to just include age cubed twice. So what software does is includes age cubed for the first term, and then for the second one, it will multiply it by log age. So let's now look at these nonlinear functions from both restricted cubic splines and fractional polynomials and compare them. So remember, lower numbers of knots are simpler functions, and an FP1 term is simpler than an FP2 function. So here we can see for restricted cubic splines, we had just simple curvature with 3 knots, and this looks very similar to the FP1 function that was selected. Now with 5 knots, we started to see a lot of curvature. So here we can see a fairly, let's say, wiggly line, which might be overfitted to some extent, but what we see is a very similar shape to what we get with the FP2, although the FP2 is smoother. So the benefits of using these approaches to modelling continuous variables are, the main aim to do this is to get a better fit to the data, because of course we want the model to predict well. So some of the relationships that would occur in real data can be fairly complex, and by using these methods we may be better able to capture these relationships. And ultimately, as I say, it's to improve the predictions that we get from the model. However, this doesn't come without a caution, as the more testing we do and the more flexibility we allow in the model, the easier it is to actually overfit to our development data. Now, that may not be the true relationship between the predictor and the outcome. And if that is the case and we're overfitting to artifacts of the data, actually we're sacrificing this better prediction, because it may lead to a model that performs really well in the development data but actually doesn't validate very well. And what I mean by that is that when we test that model in new data, it doesn't perform as well as we would expect. And this issue of overfitting is one we will talk about throughout this course. So we've looked at how we could model continuous variables non-linearly, and for illustration I've shown this for univariable models which only contain the predictor of interest. However, we can extend this to the multivariable setting when the model is fitted with multiple predictors in it, and non-linearity for a particular variable is considered in the presence of the other variables. The reason this is important is because the function you would obtain for the variable of interest could change depending on whether other factors are accounted for or not, and therefore it's better to do this in the presence of other predictors. So here's an example of this in pancreatic cancer. So this is where we were trying to predict mortality in individuals that had pancreatic cancer, looking at a biomarker which is CA19-9. So if we determined the functional form based on a univariable model, we had a shape like this. So what this says is that the hazard of mortality in individuals with pancreatic cancer, it increases as CA19-9 increases to a certain point, and then the hazard decreases again, which isn't very realistic. On the other hand, if we were to determine the functional form in the presence of the other variables, so using multivariable fractional polynomials, we find that we still get this sharp increase and then it plateaus off, which is a more realistic function and more clinically plausible. So we will come back to how to look at nonlinear functions in multivariable models later in this lecture, but for now let's move on to modelling interactions between different variables. So firstly, what is an interaction? An interaction between different variables, or predictors in this case, is where the association between a particular predictor and the outcome is not independent to the other predictors. So it's modified in some way by the values of other predictors. And where this occurs, this is an interaction between two possible predictors that modify their effect on the outcome. So an example of this might be considering the effect of treatment based on a predictive marker, so for example a biomarker, and this is said to be predictive if the biomarker values themselves tell us something about how well someone will do on the treatment. And the way in which we model an interaction is to include the main effects for both of the variables. So here, for example, we have treatment and we have the biomarker, and then we include the interaction terms. So we estimate another parameter, and this is for the interaction. So this is treatment multiplied by the biomarker value. So this is how much the log odds of the outcome are modified in addition to the main effects of treatment and biomarker. Now, it's worth considering that there are a lot of possible interactions if you were to test all possible interactions. So if we had an example where we had 5 main effects in our model and we wanted to consider all possible interactions, well, already you've got 10 possible two-way interactions. So given that prediction modelling and the development process is already, or it can already be largely data-driven, we already have to consider this issue of multiple testing, and this is made even worse by testing interactions. So if this is something that is of particular interest, well, then it's worth noting that this requires a large amount of data, and often interaction effects are considerably smaller than main effects and may be difficult to detect. And it's also worth considering the difficulty in interpretation. So it's fairly simple to interpret an interaction between, let's say, 2 binary variables. However, it's considerably harder to interpret the interaction between 2 continuous predictors, for example. So our recommendations here are that unless you have a very large data set and testing for interactions is a particular interest for your study, we would suggest limiting to known interactions. So there might be previously published evidence of some interactions, in which case do include them, or otherwise limiting to testing just a few clinically plausible interactions that may be of particular interest in your study, and therefore you're reducing this issue of multiple testing by limiting the number of tests you would conduct. And the risk is, again, if you perform too many different tests, you're likely to find things just by chance, and that issue contributes to overfitting to the data, which, as I mentioned before, can lead to poor predictive performance when we apply the model to different patients.
So let's move on now to looking at ways in which we can actually develop the model and select which variables should be included in it.
There are different ways we can select predictors for inclusion in a prediction model, and a good place to start is with clinical knowledge. So we could select all the predictors that are known to be predictive, and we could get information from previous studies and literature reviews to inform our selection of these predictors. On the other hand, if we don't have much clinical knowledge about which variables are likely to be good predictors, we could use statistical methods for variable selection. So I will go through these techniques as well. So we can use automatic selection procedures, which are based on hypothesis testing, to decide which variables should be in the model and which variables should be excluded from the model. And ideally, we don't want to use this in isolation. It should be supplemented at least by clinical knowledge. So we can combine these two strategies and specify the variables that are known to be good predictors, and then perform statistical variable selection for other candidate predictors for which there's less evidence. So here's just an example from a published study, just showing how they've reported their variable selection. So the CHIP prediction tool is for the use of computer tomography in patients with minor head injury. And here they say that they used multivariable logistic regression with backward stepwise selection. So this is the technique that they've used, with a p-value greater than 0.05 for removal of variables. But we forced variables that we considered to have great clinical relevance back into the model. So this is an example of them combining both the statistical selection methods with clinical knowledge. So something else that comes up in the literature is a method called univariable screening. And this is where researchers first look at the univariable associations between each of their potential predictors and the outcome, and then decide whether that association is significant or not. So they might define this at some level, such as a p-value less than 0.1. And then if that predictor is considered significant, they would retain it and consider it in the multivariable model. And if it's not significant, then they don't take it forward to the multivariable modelling. However, this is problematic as it doesn't look at the independent or added value of each variable after accounting for the other variables in the analysis. So for example, a p-value greater than 0.1 from a univariable analysis isn't the same as a p-value of greater than 0.1 in a multivariable analysis accounting for the other predictors. And in some cases, what this might mean is that, particularly, for example, if there's confounding, actually these p-values might differ and something could be significant in the multivariable model, but would therefore have been excluded at this univariable stage. So therefore, univariable screening is not a recommended approach when you set about to develop a risk prediction model. And a paper came out back in 1996 on this, the inappropriate use of bivariable analysis, referring to univariable screening. However, we do sometimes still see this in the literature. So we want other methods for selecting our variables. So one option is to fit the full model, so we don't perform any variable selection. We simply fit a model with all our candidate predictors. And then other options include automatic selection procedures. So remember I said these are statistical methods for selecting it based on hypothesis tests, and there are different options for how you can do this. You could start with a null model and add variables based on significance. You could start with a full model and remove variables, removing those that are not significant, or combine these two approaches in a stepwise selection approach. And there are other methods which are penalised regression techniques. So these include methods such as lasso and elastic net. And Richard will talk a little bit about these tomorrow, as these sort of include a penalisation bit. So we've included them with part of the internal validation process. So automatic selection procedures can be used if we don't know which variables should be included in the model or not. So if there isn't much clinical knowledge that can inform this. However, as I mentioned before, we can combine this with clinical knowledge, so we can perform hypothesis tests using these automatic selection procedures for some variables, whilst forcing known predictors to remain in the model. So if a variable is known to be a predictor, we're not interested in what the p-value is, because remember that's dependent on sample size and other things. So actually, if it's a known predictor, we want it to be in the model regardless of the p-value. These automatic selection procedures then use a series of hypothesis tests to decide which variables should remain in the model and which ones we can remove from the model to reduce down the complexity of the model and only keep a subset of them. And as I mentioned before, we have different options, including forward, backward, and stepwise selection. So let's first look at forward selection. Here we start with a null model. So a null model is one with no variables in it. So here we just have the intercept term. So if we're considering a binary logistic regression model. We then also have to specify some criteria for entry into the model. So often this is based on a significance level, for example, a p-value. We then consider each variable, so each of our candidate predictors in a model, and decide whether it improves the model fit or not. So if, for example, we're considering 3 possible variables, we would fit 3 models, each with each of these variables in it, and then look at how much the model fit improves. And we would then add the variable that is most significant. And then, so let's say this was variable 3, we would then consider which variable should be added next. So here, now there are 2 variables remaining, so we would fit each of them in turn, and again see which one most significantly improves model fit. And we continue in this way until no additional variables can be added. So for any other variables, they would have a p-value greater than whatever we've specified for our entry criteria. Backward elimination is the reverse procedure. So here we start with the full model, so that's one with all the variables included. So here if we have 3 candidate predictors, they're all in the model. We then instead specify criteria for exit from the model. Again, this can be based on the significance level, so for example a p-value. And we then remove each variable in turn. So here variable 3 has been removed, in this case variable 2 has been removed, and variable 1. And we test for significance. So we're comparing that full model to the model with each of these removed. And in this case now we would remove the least significant variable and then test for whether another variable should be removed. So here, for example, variable 1 was removed as the least significant variable. We would then fit models without the next variable and see whether any additional variables should be removed. And here we continue that process until no more variables will be dropped from the model. So here all other variables would remain in the model if their p-value is less than the specified level. And then stepwise selection combines these two approaches. So we could start with either the null model or the full model. So here let's consider starting with the full model. Now we've got all 3 variables in the model. We then need to specify criteria for both entry and exit from the model. So for example, specifying p-values for entry and exit, and remember that these cannot be the same, as otherwise we'd end up in a never-ending loop. So if we start with the full model, the first step would be a step of backward elimination. So remove each variable in turn and see which variable was least significant and remove that from the model. We would then look at whether that variable should be added back in. So of course in this instance, in the first step, it's unlikely that that would re-enter if we've specified different p-values for entry and exit. However, at later stages you might find that variables that were removed earlier in the process then re-enter the model later on after other variables have been removed. And we continue this process of removal and then entry into the model until all our criteria are satisfied. So there are no other variables that meet the criteria for entry into the model and no other variables that meet the criteria for exit from the model. And although there's a lot of testing that takes place when we run these automatic selection procedures, because they're based on criteria for entry and exit into the model, they're really simple to run in statistical software packages like in Stata or R, where they simply perform the series of hypothesis tests and give you the final model. It's also worth noting here that if some observations have missing values, they would be excluded from the sample for the variable selection, regardless of whether that predictor with the missing value actually ends up in the final model or not. So this is just a word of caution. Also worth noting is that depending on which selection procedure you use, so for example if you used forward or backward elimination, you could end up with different predictors being in the model. So a lot of this is just based on the order in which it happens, and there's a lot of significance testing. So we could end up in a model that is overfitted if the data is relatively small. So as I mentioned before, the inclusion or exclusion of the different variables needs to be based on some criteria that we need to define, and we can do this in different ways. So some common options are to use the Wald test p-value, which is a hypothesis test for the beta parameters in the model and test whether they significantly differ from 0. Another option is to use the likelihood ratio test p-value that compares 2 models with and without the variable of interest. And finally, we could consider a Kake's information criteria, or AIC, which is an information criterion based on the likelihood function and also includes a penalty for the number of parameters being estimated. However, worth noting that in Stata this option isn't available, so we can use a proxy for this in backward elimination, where instead we use a p-value of 0.157. So if we are to use automatic selection procedures, you might wonder which one to use. Well, the recommendation is to use backward elimination rather than forward or stepwise. And this is a recommendation based on Royston and Sauerbrei and is also recommended in the Tripod Guidelines for Transparent Reporting. And the reason that backward elimination is recommended is because by starting with the full model, we are evaluating the prognostic effect of each predictor after accounting for all other variables. So remember, this is in contrast to the univariable screening, which just looked at individual variables. Here at least we are accounting for the other variables when we decide whether each predictor should be excluded or not. So here I want to show you an example of using backward elimination in statistical software packages. Here we've got the Gusto 1 data example, so where we want to predict 30-day mortality after acute myocardial infarction, and I'm showing you an example from Stata. So if we want to fit automatic stepwise selection procedures, we use the stepwise command, and by specifying the probability of removal of 0.157, we're using the proxy for AIC. We then specify our model, so here we want a logistic model for the outcome of 30-day mortality, and we include our list of candidate predictors. Stata will then perform a series of hypothesis tests, so it will remove each variable in turn, and in that first step it will remove the least significant variable. So here we can see that smoking, which is a combination of two terms here, because smoking had three categories and we have brackets around it to keep those terms together. We can see that that had a p-value of 0.7152, which was the least significant variable, and then it was removed in that first step. In the next step, diabetes was the least significant variable with a p-value of 0.68 and therefore was removed next. And it continues in this way until all the other variables that remain have a p-value less than 0.157. So here we can see the final model with the predictors that remained in the model. So we have our list of predictors, our odds ratios, and here we can see that the p-values for all of these are less than 0.157. If, on the other hand, we had some known predictors that we wanted to force into the model, we can do this quite easily. So, for example, if we wanted to ensure that diabetes and hypercholesterolemia remained in the model, we can use this lock term 1 option. And here, so it just locks the first term in the model, so therefore we put brackets around any variables that we do want to force in, so it treats it as a single term. And now here we can see that these two variables are remain in the model, even though their p-values are greater than the probability that we specified for removal. And we can do this using multivariable fractional polynomials, or MFP, which is very similar to the fractional polynomials I showed you before, but now in the multivariable setting. So we can consider the functional form of continuous variables in the presence of the other potential predictors. And this method can do so as part of the variable selection procedure. So it uses a closed testing procedure, so it loops through different tests where first we consider whether a variable should be included in the model or not. And then if the model should be included, so that's in its most complex form, it then decides whether that complexity is needed or whether it can be simplified. So it performs tests to compare a linear function to FP1 or FP2 terms for that variable. And it does this as part of a backward elimination procedure, so we still specify our significance level for removal of the variables. So let's consider the steps of the MFP process. So because it's using backward elimination, we would begin with the full model, so including all our candidate predictors. And then as part of this closed testing procedure, the first test, as I said, considers whether the variable should be included in the model or not. And this uses a series of likelihood ratio tests, this closed testing procedure. So in this first test, we want to consider, let's say, whether x1 should be included in the model or not. So it fits the most complex form here, which is an FP2 function. So it selects the best FP2 function for variable x1 and compares this to a model that excludes x1. And this is tested using a chi-squared test with 4 degrees of freedom. So that's 1 degree of freedom for each beta term and 1 for each power. Then, based on that, if x1 is not excluded from the model, we move on to the second test as part of the procedure, and this is whether variable x1 should be non-linear or not. So now it takes that function from the previous test, so this FP2 function for x1, and compares it to a model in which x1 is fitted linearly, and this is tested against a chi-squared with 3 degrees of freedom. If the FP2 term is significantly better than the linear function, then the third test compares the nonlinear function, so this complex function of FP2, compared to a simpler nonlinear function, which is the FP1. So that series of tests is repeated for each variable considered in the model, and of course for categorical variables it's just simply a test of whether the variable should be included or not. But for these continuous predictors, it selects the best FP2 or FP1 term, and that's considered to be the one with the lowest deviance. And by conducting these tests in that order, it's done so to preserve the nominal type 1 error. So let's now look at how we can do this in statistical software, again just illustrated in Stata, and within the practical you will see how to do this in R as well if you're an R user. So within Stata we can use the mfp-a command, so this is just an extension to the original mfp command. We specify our significance level here, alpha of 0.05 for the series of tests, and we can specify our exclusion criteria p-value. So again, we're using 0.157 as a proxy for the AIC, and this part of the code is very similar to before. So we're fitting a logistic model to our outcome, and we include the list of candidate predictors. So now let's look at the testing procedure for a particular continuous variable. So let's consider age. Here the first test that is carried out compares the null model, so that's the model without age, and it compares it to the most complex function, which is an FP2 term, which here was selected as the powers of -2 and 3, and here we can see that this p-value is significant. So the FP2 function was significantly better than excluding age from the model. The second test then looks at comparing the FP2 function to the linear function. So here we can see that the p-value is again significant, and therefore the FP2 function, so the non-linear function, fits significantly better than the linear function. So the third step then is to compare FP2 to FP1 to see if that extra level of complexity is needed or whether just a single fractional polynomial is required. And here we can see that the p-value is 0.546, so this is greater than our alpha value here, and therefore the FP1 term is sufficient. And we get here the list of the predictors included in the final model and the functional forms for all the continuous predictors. So here, of course, we've got some binary variables. So sex here, it just says power 1, but that's just whether it's included or not. Age is a continuous variable, which we looked at, so a single power was selected for that one. And we've got some others, so some variables might be excluded from the model, so they just show status out. And here it looks like the only nonlinear function that was selected was age. The output also shows us any transformations of the continuous predictors, so we know how it's modelled. So here we can see that age was modelled as age to the power of 3 minus 221. So this is where the variable is centred. And also age was rescaled prior to this, so x is age divided by 10. And another variable here was also centred. And then finally we get our parameter estimate. So here are the variables included, some of which have been transformed, and we get our odds ratios, and we can see that the p-value is less than 0.157 for all of these variables. And finally, I just want to raise this issue of overfitting. So I've mentioned it a couple of times already, and it's something that will be mentioned a lot more over the coming days. So Frank Harrell once said that carefully fitting an improper model is better than badly fitting and overfitting a well-chosen one. So that's just something to think about. So what is overfitting? Well, this is an issue that's closely related to the sample size, or our effective sample size, which remember relates to the number of outcome events we have. And overfitting can occur where we fit a model that is too complex for the amount of data we have. And this problem can arise due to lots of significance testing. So for example, if we're performing a test for variable selection, if we're also looking at including nonlinear functions, remember it's fitting lots of different tests to decide on the best nonlinear function to use. And we may also be using additional degrees of freedom in modelling the baseline hazard for survival data if we're using, let's say, flexible parametric approaches. And what happens then is that we might end up too closely modelling the data at hand. So we end up modelling some of the noise rather than the true relationships that lie underneath that data. And due to all this testing, we might end up finding some spurious associations simply by chance. So it's important for us to consider how many parameters are being estimated and how many tests we're conducting, because remember, this doesn't just relate to how many variables end up in our final model, but rather how many we are considering at the start. And also how many events there are. So it's the number of tests relative to our effective sample size. That's important. So model overfitting is more likely to occur when our sample size is small. So in other words, when there are few events in our data set. And this is because it's relative to the number of predictors versus the complexity of the model and the number of tests that we are performing. Considering our Gusto 1 dataset, so remember we had 135 events in that dataset and we considered 17 variables. So actually here, if we had to calculate our EPV and consider the fact that we were looking at nonlinear functions as well, well, we would expect that overfitting is actually quite likely in that dataset. So what would happen if we had even less data? So if I was to now take a smaller sample, so just a random sample of half of that data, so we would expect about 75 events to occur, and we had to repeat that MFP process. So in the full data, remember this was our model and we had a cubic function for age. If we had to take a random sample of half that size, we might still get the cubic function, but now we can see that, for example, sex, the effect looks much larger. If we had to take a different random sample, we might see something very different as well. So here we can see that some associations appear much stronger than the original model in the full amount of data. And on the other hand, the functional form might change as well. So here we had a cubic function, whereas if we had less data, we might not detect that cubic function. And finally, we might end up with some additional variables being selected purely by chance. So why is overfitting important? Well, remember that our aim is to develop a prediction model that performs well and can be used to make predictions for new patients so that we can use it in clinical practice. So these predictions need to be valid in order to use the tool. And if the model is overfitted to the development data, well, then those predictions won't be valid outside of that development data because it models it too closely. So if we test that model in new data, so for example in an external validation study, well, actually we don't expect it then to perform as well as in our development data. So we refer to this as optimism. So when overfitting occurs, performance of the model in that development data is likely to be too optimistic compared to what we would see in a different data set. So what can we do about it? Well, there's some steps we can take earlier on in our decision-making process as part of model development. So we need to firstly consider how much data we have available and how many events we have. We can also consider how many predictors we have and reduce that number if necessary using the data reduction techniques I mentioned earlier. And we can also carefully consider our model development approach. So we may need to simplify things. Perhaps we shouldn't be looking at nonlinear functions for every single variable or really complex functions, as this increases the number of tests that we're going to perform. And also remember, supplementing any statistical approach with using clinical knowledge also aids this. But crucially, we need to make sure that we evaluate our predictive performance of these models, and we can do so in the same data, so in our development data, and this is referred to as internal validation. And this is very useful in evaluating how likely overfitting is to occur. So by resampling, we can actually estimate the likely optimism in our performance. And we can do something about this too. So by estimating that optimism, we can adjust for this by shrinking the regression coefficients to account for the optimism. So just one final thought then, and this comes from John Copas. He said, a good predictor or model may include variables which are not significant, exclude others which are, and may involve coefficients which are systematically biased. So here, remember, some variables, those that are known to be predictors, may not be significant in our data. And also here he refers to the systematically biased, so we might have to shrink our coefficients and actually bias them in order to improve our predictors in new data.
So to conclude then, in this lecture we've looked at how we can model different types of variables such as binary, categorical and continuous variables. I mentioned that it was best to avoid categorizing continuous variables as it results in a loss of information and isn't necessary for prediction modelling. Instead, we could consider nonlinear functions for continuous variables using methods such as fractional polynomials or splines. When looking at how to model continuous variables non-linearly, it's best to investigate this in a multivariable model to select the functions after accounting for other predictors. Also, it's a good idea to use clinical knowledge rather than relying purely on statistical testing. So even if the variables are non-significant in the modelling process, if there is enough evidence supporting them and they're known to be predictors, they should be included in the model anyway. If you're considering using automatic selection procedures, remember that backward elimination is the recommended approach, because here, at least you consider the effect of each predictor in the presence of all others and can account for any possible confounding. We'll also look at other methods for modelling and variable selection, such as lasso, later on the course. And finally, I've introduced you to this idea of overfitting and how likely it is if we're performing lots of hypothesis tests. So fitting the model is only a fraction of the work, and evaluating our process and the performance of the model through internal and external validation is key. Evaluating the model is so important, in fact, that we spend the majority of the course talking about validation and related topics. So tomorrow we'll focus on internal validation, and you'll also see how you can shrink your coefficients to account for optimism. So thank you all for watching, and I hope you enjoy the other sessions on the course.